All right, line A4, learning task 7. We're going to go and take a look at describing parallel RLC circuits. So circuits that contain all of the stuff we've covered so far: resistance, inductance, and capacitance together. They give us this picture to begin the entire module with. And what they're doing in this picture is they're just drawing a parallel circuit in a little bit different of a manner than what we're used to. You're probably quite used to circuits that look something like this. Just pull that one out and draw that line up there, this line up here, this line up here. And this is the standard way that we go and draw our circuits. Now, they've drawn this one specifically like this by dropping these this top bar down there and running a single line in. What they're showing is they really just wanted to be able to demonstrate that we're going to go and have a reactive current that is going to be part of our circuit. We're going to go and have a total current, IT, that is going to be made up of my IR, the resistive component of my current, and my IX, my reactive part of my current. Now, we don't know yet at this point, because there's no values that are attached to this one, which one of these is going to be larger, whether IC or IL is going to be larger. But one of these is going to be larger than the other, unless they're resonance, in which case they're both going to be equal. Whichever one of these is larger is going to go and become that reactive current type that we would have. For example, since they're in opposition to each other, and this is just going to be, me throwing numbers out there, they're not part of this thing yet. But if I had a capacitance that at 50 hertz was going to go and give me a sufficient XC, I might be developing a current that might be, we'll give this thing 10 amps, and I might be, for the same frequency, having an inductor over here that might give me a value of 12 amps over here. And what I would be able to do at that point is I would be able to say, well, 10 amps is going to get canceled out by each other. They're basically going to go and pass 10 amps back and forth, and my IX would therefore have to go and become 2 amps. My total net amount of reactive current, that's really what they're looking at over here, is a net value. The net value will be 2 amps, because this 10 amps is going to cancel out 10 out of this 12 over here, meaning that my supply only has to go and give a little bit of inductive reactive current over there. This is going to go, or this cancellation, this effect that we are going to go and have off of here is going to lead into that whole power factor correction thing that we're going to look at. And this type of a circuit setup, parallel circuit, is going to be a really common type of circuit setup for us to go and have. We know that that's what we connect almost every circuit out there as. Because we use this parallel circuit so many places, we should be familiar with what our voltage values are going to be. We know for a parallel circuit, voltage of my source is going to equal whatever I've got across my resistor, is going to equal whatever voltage I have across my inductor, which is going to equal whatever voltage I'm going to have across my capacitor. So it's going to be really easy for us to go and once again establish powers that we are going to go and have off of our individual components, right? Using that whole E squared over top of R power formula, we are going to be able to go and establish power here, which is going to be a VARS L, and power here, which is going to be a VARS C. We're also going to be able to go and establish by finding out our impedances, so the individual resistance that I have here, my XL over here, and my XC over here, I would be able to go and figure out my IL and my IC. And then I would be able to go and add these things together. We've gone through why we've got capacitive current that is going to be leading, why we've got inductive current that is going to be lagging for a parallel circuit. But for those of you that don't remember, the reason for it is that we know that resistive current, IR, is going to be in phase with my V applied, right? Whatever we put onto the circuit for voltage. And then we know that if I'm looking at Eli, the Iceman, that we would be, if we were standing on the voltage and looking backwards, we would see our current. Therefore, it's going to be a lagging IL. And if I were standing on the voltage and looking forwards, we would see that I'm going to have a leading IC. Close those arrowheads off, IC, and here's my IL. So we're going to go and use that convention, IC going to the top for a parallel circuit, IL going to the bottom for a parallel circuit inside of these. What they're showing off of the next set of drawings is just simply vectorial addition. There's nothing new here that we have not covered before. All it is that my total that I'm going to go and have, this is the sum that we get out of there, is going to be made up of my resistive. I'm going to add that tip to tail with my inductive, add that tip to tail with my capacitive. In this case, we see that it is a highly capacitive circuit that we have over here. We get a lot of capacitive current, therefore I'm going to go and have an IT that is going to be overall net capacitive or net leading that I'm going to go and have. You could also go and add through it in the opposite direction, go IR, then go up to your IC, and then come down from your IC onto your IL, but you still end up at the same net vector that we would have off of these ones. In other words, my total net amount of current, if I've got a larger IC, my net amount of current is going to be up top here, and my triangle is going to be up top here for that capacitive type of circuit. If I've got a larger IL, we just see that off of this one. Almost the exact same, just go in the opposite direction. We do our resistant current, we do our inductive current, we come back on our capacitive current, and then that all together gets us our net value of current. Over here, they're just doing an opposite order addition, tip to tail, but coming out to the exact same result off of these ones. They do show inside of your binder, that you can subtract these things, or that you can go and use Pythagoras, or all sorts of things like that to get around to them. We're going to primarily, once again, use vector addition, put everything in at the angles. Find out what our component is, identify the angle. Once we've identified the angle, put it in at the proper angle and add them all together, and we will get the correct answer. The three triangles that are shown over here show what our circuit is going to go and look like based upon whether we have got a larger inductive current or a larger capacitive current that we are going to have. The first one over here, I see that the larger one, color there, the largest one of these that I have is going to be my inductive current. Therefore, this is going to be an IT that is going to be a lagging type of overall current. This one over here, I see my IC is the largest one, so I'm going to have an IT that is going to be a capacitive or a leading type. This one over here has got the same value of IC, but now we've got more IL against it. And as we've got more IL against it, we see that my IT starts to go and shrink down. Now, if you were to go and physically take a tape measure and compare this IT and this IT over here, you would see that this one over here is going to go and be smaller. And if I continue to go and increase my IL like that, I would be able to go and push this thing all the way down until eventually my IT was going to be the same as my IR. You should recognize that at that point, where you've got the same amount of capacitive current as inductive current, you would be at resonance. We've talked about this before, where they are going to be equal and in opposite directions. The big difference is that when we are dealing with a parallel circuit that is going to be in resonance, inside of a parallel circuit, my IT is going to be at a minimum. IT minimum. Whereas when I was dealing with a series, my total amount of current was at a maximum. And I don't know if you remember that graph before, but we saw that one for a series one where we could go and have that tuning curve that could rise quite steeply. When we're dealing with parallel resonance, we get far better characteristics out of it. We're going to go and get this minimum value of current, which is in a lot of cases really what we're looking for, right? We don't want to go and pick, the high amperage component if we've got a low amperage component, because all of that eats up space on your service, and then you have to go and change your service or upgrade and stuff like that. It gets expensive. We always want to be as efficient as possible. Right underneath all of these triangles, they also show you some a little blurb about impedance. Once again, in a parallel circuit, we should not be fooling around with impedance. Impedance is mathematically workable. However, when you just look at that formula that's underneath there, look at it. It's just like inverted roots, inverted squared, etc. It's just a ridiculous looking formula. If you imagine the number of brackets that you'd have to put in and the number of places where you could forget to put in a bracket and accidentally drop a value that you're trying to put together, it is just not worthwhile trying to go and do that calculation. You could do it as an inverse of your polar format, but once again, trying to learn that method, although mathematically valid, is not worth the effort. Just stay away from the impedance in parallel and work with the power that we are going to have. For power and for phase angle, we are going to go and utilize these circuits. Now, once again, inside of here, they don't show us power triangles inside of this whole learning task, and that's because our power triangles are going to be flipped. They're not going to be following the same convention that we see over here where, the IL is going down and the IC is going up. So they just kind of talk about parallel at this point, talk about power and phase angle at this point and say we can use multiple different ways to go and get it. We can go and use our I squared R through an individual branch. We can go and use our, volts times our amps through a branch, etc. The one that we are going to prefer to use is once again going to be that E squared over R, because it just does not rely on us having to find that current. We find the resistance or the reactance, which are easy to do, and then all we do is place that E over top of it. Power factor inside of a parallel circuit is going to be treated the exact same as every other type of circuit that we have dealt with so far, which is that my power factor is going to be my ratio of my true usable words, my watts, over top of my VA, the total apparent power, which is the vector sum of my watts and my VARs together. Basically, the less VARs we have, the smaller the VA is going to be, which means that our power factor is going to be better. We've done a bunch of calcs on that, small calcs working our way through. We're going to get to some bigger ones as we get into this whole impedance and power factor thing. The next little section inside your binder talks about parallel resonance. And parallel resonance is really cool inside of a parallel circuit, because what we have is we get cancellation of our current. If you take a look at this IL and this IC, we see that they are going to be at the same value. We see that there is inductive current, there is capacitive current, but they're happening at opposite times. I don't know if you remember going through the early sections of inductors and capacitors, but where we would take a look at a voltage, and then we would say that if I'm going to be dealing with a inductor versus a capacitor, we're going to go and have either leading currents or we are going to go and have lagging currents. Right? We're drawing a here. And then we will draw in one more current over here. Like that. It's poorly drawn, I know, because I'm freehanding, but it kind of gives us an idea as to what we expect to go and see off of these, particularly that section is poorly drawn, but whatever. You should be able to go and identify each of these. If this is going to be your voltage, we see that by the time that this voltage gets through here, this current has already done that. Therefore, this would be my IC. And we see that by the time that my voltage has risen, this one over here is going to be lagging that quite a bit. Therefore, this is going to be my IL. So what we should see, if I had drawn these things much more better, we would see that my inductive current is in the negative, while my capacitive current is in a positive. And then over here, and it's, once again, this is a poor crossing that I've drawn here, I would go and see that my inductive current, inductive current would be at a maximum, while my capacitive current would be at a maximum in the opposite direction, and both of them would go and cancel out and cross over here. Really what's happening is I'm feeding current back and forth from one to the other. When one of them is in a positive, the other one is in a negative. Now, if I'm going to go and have to, take from somewhere, I can either go and take current from a source, which is going to go involve work, or I can take current from something that is expelling current already. In the case of my inductor, I can take current from my capacitor, and from my capacitor, I can take current from my inductor, because we know that they're always going to have opposite needs. When this thing needs current, it is going to be able to go and take that current back from this capacitor over here. So we're going to go and get current that's going to go through in this direction, and then on the next alternation, this one's going to have its current flow reversed, and it's going to be going through in the opposite direction. And so really these two kind of just form their own little sandbox, and they play in it together. Initially, yes, when we power on the circuit, we are going to have a inrush amount of current. We're just going to get a blip of current that's going to come in, and it's going to go and charge up my capacitor initially and expand my magnetic field. But after we've sent that first initial group of current of electrons into there, what happens then is that these two just pass that current back and forth from one to the other. Literally, that is all that is happening inside of a parallel circuit over here. We still have the same amount of VARs that are going to be developed off of here and the same amount of VARs that are going to be developed off of here, but they're now just going to be provided by other components other than the source. If I was at a complete parallel resonance, and we'll do some of these calculations later on, we'll take a look at current values inside there, what I'm going to see is that my source is supplying all of this current over here, and that these two are just going to be supplying that current back and forth from one to the other. Now, it seems pointless because we don't know enough about our overall electrical systems yet, but we do have a lot of electrical systems that are going to be inductive. Ballasts, transformers, and then motors are all going to need to use magnetic induction to go and operate, to transform voltages, to create light, to go and create rotational movements, etc. Because they're all going to be inductive, we don't want to leave those inductive bars loose on the system, so in a lot of cases we're just going to place those caps on it to go and cancel those things out. We will cover that in depth through the last sections out of this learning task A4. We're going to go into all of that power factor correction at that point. But for now, just know that that is where we're heading with all of this. Okay, going back to what we had over here, my total amount of current that I am going to go and have when I reach when I reach parallel resonance is simply going to be my resistive current. It is the only current that we are going to go and see out of our system. IT is going to be equal to IR. We saw that over here inside of this, right? My total amount of current is only the resistive current because these two are just passing current back and forth between the two of them. Do note as well that it's going to be our absolute minimum value. Highlight that section because this is, a complete opposite to our series. Our series, we had the maximum amount of current at resonance. Now for my parallel, I am going to go and have the minimum. As far as my power, when I'm at resonance, if I'm going to go and have any VARs that are going to be developed by this and any VARs that are going to be developed by this, they're going to get fed back and forth. I don't know if you remember those drawings that we had before where we said that we had our voltage waveforms and then we took a look at the power waveforms that we had and we saw that an inductive waveform looked like this. It was double the frequency. This was my inductive VARs C. And then we took a look at my capacitive and my capacitive. Try that again. My capacitive bars looked like that. Bars. I keep saying the wrong word here. It's really hard for me to draw and talk at the same time sometimes. Bars L. Okay. That's what I was trying to do before I kept stumbling over top of my words over here. But my total amount of inductive bars are going to be opposite to my capacitive bars that I'm going to go and have. That black line represents my voltage. This is going to be my VARs L. I see that my VARs L are giving back while my VARs C are taking in. So instead of taking from the source, my VARs C will take from my VARs out. And then over here, I'm going to go and see that in the next instant, I'm going to have my VARs C that are going to be giving back, and then my VARs L are going to be receiving. And so we have all of our bars that are going to be canceled out. What that means is that as far as my source is going to be concerned, my source really is then only going to go and see this current, which means that it's only going to go and see its watts. In other words, at resonance, my VA is going to be equal to my watts. It is the only thing that I will see, which means it's going to have a 100% power factor because they're both the same. Watts divided by VA, if they're equal, would obviously equal 1 or 100%. As far as frequency goes, move this thing over to the side here. Frequency is going to go and make a difference as to where this thing is going to go and resonate at. For any combination of inductors and capacitors, there will only ever be a single resonant frequency. We can calculate that one using that same formula that we had before. FR is equal to 1 over top of 2 pi root LC that we are going to go and have off of that. Find my inductor value, find my capacitor value. You'll note it is the same formula as what we were using inside of our series circuit. Once you know those in millihenries and in millifarads, microfarads, whatever size of cap that we're placing in there, you can then find your resonant value of frequency off of these. Over here, they show you two graphs. These are two separate graphs. They're being superimposed onto the same one that we are going to go and have over here. What they're showing us is the amount of current over here based upon the type of circuit that we have. And really, this is the RLC that we're looking at. There's my inductor, there's my capacitor. What they're talking about is this resistor, whether that resistor is going to be low resistance or it's going to go and be high resistance. If I have got low resistance, my current is always going to be high because there's going to be a lot of current that is continuously passing through that resistor, loads of it. And so I only get a little bit of it that's going through these ones. And so when I balance them, I don't see much of a change whatsoever. But if I go to a high value of resistance over here, that high value of resistance means that there's only a trickle of current that's going to be going through, which means that resonance, if that's the only current inside of my circuit, that there's going to be very little. As soon as I move away from resonance, either upscale or downscale, whichever one it's going to be, if I move away, I'm going to start to allow current to pass through these. Instead of these two passing current back and forth, which is what's happening when they're at resonance, now I would start to go and take current in from the supply to go and feed those, which is why my current starts to rise as I move away from these in either direction. Once again, what we want to have for reaction out of our circuit is going to be very much based upon what the circuit itself looks like. This one over here, if I'm going to go and have this type of a tuned circuit, what I'm looking to try and do is drop total amount of current. So I might be trying to go and filter out certain specific frequencies that I don't want to go and have, third order harmonics. This type of a circuit over here is going to be great for some of that third order harmonic frequency that you're going to deal with inside of your third year. Once again, when we get to third year, you've got me as an instructor. We're going to refer back to this. I don't know if the other instructors all do, but I know that I make a point of coming back to this theory because this is where that applicability is going to come in for them. Okay, the last part that we have over here deals with a practical inductor. We know that we live in an imperfect world where we have to use physical components, which means there will always, always, always be some resistance inside of our inductor. And so we are going to go and have practical inductors. We do this dotted line representing the resistance of that inductor and the actual XL, the inductive reactance of it. Together, these are going to go and create a Z. Now, we don't want to go and use that Z because we would have to do that inverse parallel Z and XC and R and all that other stuff, so it would be a bunch of pain. What we would want to do for this is either break it down into watts and vars, which would be one way to deal with it. So watts 1, watts 2, vars L, and vars C. If I were to do that, I would be able to go and add all of my watts together, all of my vars, and my counteracting vars, and I'd be able to figure out exactly how much power I've got inside of that circuit, my total VA. The other way that this circuit is solvable is to go and find my values of current that I'm going to go and have. So for this one over here, I know that it's fully resistive, so it is going to be IR at an angle of 0 degrees. This one over here is going to be IC, and it is going to go and be at an angle, right? We have to be a leading one, so it's going to be at an angle of 90 degrees positive. This one over here, I'm not going to break into two individuals. I'm just going to go and find my IT of this over here. And IT of this one is going to be somewhere around negative 90-ish. Depends on how much inductive compared to my capacitance that I'm going to go and have. But all I need to do then is take those currents, this one around negative 90-ish, this one at 0 degrees, and this one at 90 degrees, add them together, and I'm going to be able to go and establish the total net amount. That is what we are seeing on this one over here. They have a bunch more errors inside there that we don't need to necessarily take a look at. But if I take a look at this, I see I've got IR, my resistive value of current. Then I see I've got my IRLs, the inductor that I'm going to have. It's at not negative 90 degrees, but it's close to 90 degrees. And then I'm going to go and have my IC like that, which is going to be going up at positive 90 degrees. And so they're just adding these things tip to tail. tip, 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 like that across, and we end up with this net amount. This net amount over here, this triangle over here would be my total current that I would have for this circuit over here. Once again, we'll do some of those calculations, make sure that we're able to go and easily do those. That's going to be inside of our next learning task number 8. Learning task number 8 is going to be a long and a beefy one because we have a lot of calcs to go through off of it. But we will use that calculator where we can to go and take all the shortcuts that we can, because ultimately we just need to be able to go and solve for them. All right, that's it for this one.